Here we are at part 2 of our reductions mini lectures. I'm trying to reduce the length of these mini lectures, but I guess that means I'm increasing the number of mini lectures. Anyhow, if you have some feedback, let me know. So, reductions, focusing on the addition of hydride, H-. Last mini lecture we covered the addition of lithium aluminum hydride and sodium borohydride. Now we're going to look at two more hydride reagents and see how they're the same and different. But before we do that, let's look at a couple of examples. So here's some kind of ridiculously hairy looking molecule with some new reagents that I'm not real sure about. Alright, so we look at this, we analyze, we say, what the heck is this thing? And what I'm going to focus in on is AlH4-. That many hydrogens, it's got to be a reducing agent, anionic. There's my hints that I'm talking about adding a nucleophilic hydrogen. So that's fine, but good Lord, what am I adding to over here? So you need to find an electrophile. And frankly, we got electrophiles up the wazoo here. We've got an acidic hydrogen on the nitrogen. We've got an acidic hydrogen on my hydroxyl group. And of course, we have chapter 17's electrophile, that ketone. So what's the story? Well, the story is that actually we're going to reduce the ketone. Now, that's not to say that we don't deprotonate the nitrogen and the oxygen. After all, acid-base always wins. But, how is it that we get the alcohol in the presence of those acidic hydrogens? Keep in mind that these are tetracoordinate. So when I add one equivalent of lithium aluminum hydride, I'm actually adding 4 equivalents of hydrogen. So in fact, it is extremely likely that I am deprotonating this and deprotonating this, and I still have plenty of lithium aluminum hydride left over to go ahead and reduce my ketone. Alright, so example number 1, I reduce the ketone to give the alcohol. Note that I've shown that with a squiggly line to indicate I would have both the R stereocenter and the S stereocenter, and they would not be formed in equal mixtures, but it's going to be pretty darn tough to predict what the exact ratio would be. Example number 2, again, this highlights the difference between lithium aluminum hydride and sodium borohydride. In the first example, I absolutely positively must show there are 2 separate steps. I cannot use lithium aluminum hydride in the presence of a protic solvent like water. It will go boom. Alright, so don't go there. Now, sodium borohydride, nice and mild. Again, we can, for mechanism purposes, we can just think of H-, looking for that place where it will find an electrophile and reduce it to give the alcohol. Will this be deprotonated? No, not to any appreciable extent, because sodium borohydride is so darn mild. And so our product is, in this case, from the aldehyde, the primary alcohol. And, you know, of course you're getting the alkoxide when it attacks. So that's giving me CHHO-, and then that gets protonated to give you your alcohol. Well, now what? Well, now we look at NADH, which you are full of. We are full of all kinds of things, and NADH is one of them. Nicotinamide adenine dinucleotide in its reduced form. So that reduced form means that there's a hydrogen on it. And being a biomolecule, it's one big hairy scary thing. It's a big piece of stuff. Lots of organic spaghetti on this puppy, but this is the business end of the molecule. So just to go back real quick, this is what we're looking at right here. That is where everything happens. So let's get more real here. Put in the important bits and bobs, and the bits and bobs include that lone pair and those hydrogens. Hint, hint, hydride. We're going to deliver hydride here from NADH. So when I have an electrophile, a carbonyl, of which we have multiple carbonyls in our bodies, trust me on that one. Basically, what we're looking at is popping that lone pair into the ring that pushes this pair of electrons over and kicks out that H minus to deliver it to the electrophilic carbonyl to give me my reduced product and an aromatic ring. This is NADH. NAD, just the plain old nicotinamide adenine dinucleotide. You'll see it in biochemistry as NAD+. Reducing agent here, right? Delivering H-, oxidizing agent on this side of the equation. NAD+ is an oxidizing agent. And what's really important to note is that we've created a stereocenter, and in a biochemical system, we do this, Mom Nature does this stereospecifically. So I will not get an equal mixture. I will not even get a mixture of any sort. I will get stereospecifically one enantiomer. The reason why that is shown here in this kind of quick and dirty, let me talk to you about biochemistry cartoon. I'm not going to go into this in any kind of detail, but what you want to see here is that I am holding my substrate in some kind of three-dimensional pocket of an enzyme. And that holding is based on electrostatic attractions, just like we learned in Chapter 1. So I've got some positive charge here that coordinates to my carbonyl on my substrate. I've got clearly lots of electrostatic attractions here between this carboxylate and this protonated asparagine, I think. I'm not sure of that amino acid. No, that's arginine, I think. But anyhow, point here is substrate being held in a specific position and NADH right nearby. And so when NADH does its thing, oops, try that again, pops those lone pairs in, pushes that pair of electrons over and kicks out H1, it's going to approach from only one side of that carbonyl, and therefore I get only one enantiomer of the reduced product, the alcohol. So biochemistry is fascinating, but keep in mind it's all just the same old mechanism as you're learning with small molecules like, say, ethanol. All right, well, that just leaves us with one more hydride reagent, and that is sodium hydride, which, as I've said before, is, something we've seen before. And unfortunately, sodium hydride, when reintroduced in this chapter, kind of muddles the waters. Well, how about muddies the waters? It's counterintuitive how it behaves. I mean, it looks like, sure, come on. I've said from day one, throw out your spectator ion, there it is, it's H-. So it makes perfect sense that it should reduce, and it doesn't. Okay, it's totally counterintuitive. So when we have a carbonyl and we treat it with hydride reagents, we actually have electrophilic sites at two places. We have, of course, the carbonyl carbon, which is where reduction takes place, but we also have the fact that the alpha hydrogens can be deprotonated to make the enolate, and we've seen that for a long time. So now we see that when I add something like lithium aluminum hydride or sodium borohydride or NADH, well, I get reduction. But when I add sodium hydride, I do not get reduction. It does not go there. No, my sodium hydride goes straight for the acid-base reaction. Now, what this is telling you is that I've been lying to you all the time. I've just been trying to keep things more simple. Basically, what it boils down to is, yeah, actually, the spectator ion does matter quite a bit. And so we can't really just ignore it anymore. Sodium is not a good cation for coordinating to the oxygen. Up here, when we're looking at these reductions, let's use this guy. Okay, so my oxygen is coordinated to the lithium aluminum hydride, and that holds the H minus close by, so it gives you the reduction product. But the sodium hydride, it is not coordinated to the carbonyl, and so it just goes straight for the acid-base reaction, which again wins, and that's why sodium hydride is a base and not a reducing agent. So some fine details here. All right, to summarize, lithium aluminum hydride is the elephant gun of all hydride reducing agents. Used with care. It will reduce ketones and aldehydes easily down to alcohols. Sodium borohydride, nice and mild. It's not going to be a problem if you even want to use that in a protic solvent, no problem. NADH, well, you're not going to use that in a beaker, but it's happening in you even as we speak. All three of these reduce carbonyls down to alcohols, whereas sodium hydride, it's different. It's a hydride, and we can think of all of these things as H minus, but it doesn't reduce, it just makes the enolate. So next we look at a new nucleophile to add to the CO double bond, organometallics. But first, here's an interesting fact. The oldest computer can be traced all the way back to Adam and Eve. Sure, it was an apple. Very limited memory. Just one byte. And then everything crashed. Ooh, all right, that's it for hydrides.